Good afternoon, dear audience. I am very glad to be here to present our work 100 Phones, a large VI Slime dataset for augmented reality towards mass deployment on mobile phones. This work is jointly conducted by Zhejiang University and SensorTime Research, all from China. My name is Yuan Jun, and I am a researcher from SensorTime. In this work, we propose 100 Phones, a large VI Slime dataset consisting of 350 sequences collected by 100 different models of phones, aiming to promote the mass deployment of VI Slime for AR on mobile phones. First, let me introduce the necessity of our 100 Phones dataset. As we know, VI Slime is a key technology for augmented reality, which allows the AR device to recover its 6-stop motion in real time in order to render the virtual content with the corresponding pose. In recent years, dedicated AR glasses have been developed offering excellent AR experiences, such as Microsoft HoloLens 2, Apple Vision, and X-Real Light. However, these devices are still in an early state and have not been widely adopted. The mainstream AR devices are still smartphones. We can experience AR game, AR navigation, and so on, while AR performance on smartphones depends on different VI Slime algorithms, camera and IMU sensors on smartphones, CPU performance, and memory of the phone, how we hold the phones, and some other factors. The existing VI Slime methods only perform well on high-end phones, but poorly when deployed on a large stock of mid- and low-end phones. Currently, the most widely used visual inertial datasets are Kitty and Durac, which are collected by Car and MAV respectively. They are not suitable for AR, as AR devices are usually handheld or head-mounted, which have different motion patterns from cars or MAVS. LSFB and Lamar both collect glass in mobile phones dataset for AR, but AR glasses usually adopt global shutter fisheye cameras and high-quality IMS, whose sensors are different with mobile phones. Moreover, the two datasets only use one or two mobile phones to collect data with high-quality IMS. In this work, we focus on smartphones whose cameras are typically rolling shutter and pinhole with small field of view 5, and IMS are of lower quality. More importantly, different phone models may have large variations in their sensor characteristics. Existing visual inertial datasets only cover one or a limited number of devices, making it impossible to reflect the robustness issues of VI Slime methods when deployed on a large variety of phone models. We propose a visual inertial dataset covering 100 different phone models to fill this gap, considering of the distribution of price, processor performance, and memory. We select 10 sensor metrics that are closely related to VI Slime to analyze the sensor characteristics of the 100 phone models. The sensor characteristics among these 100 phone models vary greatly, posing unprecedented challenges for VI Slime methods. Intuitively, high-end phones have better image and IMU quality than low-end phones in all aspects. We further investigate whether there is any correlation between different sensor metrics. We observe a rough linear correlation among reprojection error, gyroscope noise, and acceleration noise. A cross-linear correlation between the IMU noise and IMU bias can also be observed, which indicates that the phones with better data quality usually have IMU biases adjusted to a lower level. We don't find obvious correlations between other characteristics. This makes it more complicated to deploy a SLAM method to different models of phones with sensor characteristics that may vary randomly. We choose steamver tracking to 0.0 to obtain ground truth pulses for its portability and GM-level accuracy in small scenes. Specifically, we place the steamver base stations 8 in the scene and rigidly mount the phone and Vive Tracker 9 together. We follow the method of which temporally and spatially align the ground truth trajectory of Vive Tracker to that of IMU. As a result, we can get the ground truth trajectory of IMU sensor in a mobile phone. We designed 3 simple yet typical motions to collect 3 sub-datasets in a small-scale scene. Each sub-dataset contains 100 sequences collected by the 100 phones. As shown in the video, circle, the operator is walking around a 2 meters radius circle twice. Line, the operator is walking forth and back along a 10 meters line. Rotation, the operator is rotating in place for 1 minute. Those are typical motion patterns during air tourism and air navigation. The first three sub-datasets mainly focus on the robustness to different phone models. We designed the fourth sub-dataset for the robustness to large-scale scenes and general motions. We select 5 phones. Each collects 10 sequences. Each sequence has 2K15K frames and moves 70,500 meters, resulting in 50 sequences, as shown in the video. We use the method proposed in the EU to obtain ground truth in the large-scale scenes. The method is based on reconstructing an accurate visual map of the large-scale scene. For each visual inertial sequence captured in it, the ground truth pulses are obtained by joint optimization, taking both the visual localization in the pre-built map and visual inertial constraints. We use the absolute positional/rotational error (APR) and the relative positional rotational error (RPE) (RRE) that are commonly used to evaluate the performance of VI slime. Besides, we propose a novel metric or deviation to evaluate the error effect, because these traditional metrics cannot directly reflect how stable the error effect is seen by the user, as shown in the formula, where Ft x projects a 3D vertex x of the virtual cube to the image by camera pulse t. Similar idea has been proposed in Ichikari. The difference is that our aim is to reflect the accumulating error within a subsequence, rather than the absolute pulse error of a single frame. Specifically, instead of aligning the whole trajectory, we align the coordinate system every 10 seconds. Although we have calibrated the camera IMU time offset for the 100 phones in our dataset, it is not feasible to pre-calibrate every phone in practice when it comes to mass deployment. To analyze the impact of time offset, we employ the two systems VINS Fusion and OpenVINS, which support online temporal calibration. In contrast to previous works that only use MSE to compare accuracy, we propose to use the cumulative distribution function CDF to compare robustness simultaneously. A point x, while the CDF curve denotes the probability of having an error less than x is y. The curve above has better accuracy and robustness than the curve below. If time offset is not handled green curve, the result is the worst. Either online calibration blue curve or offline synchronization red curve can significantly improve the result. There is still a gap between blue and red curves, indicating that there is still room for improvement of online calibration. To run VI slime, it is necessary to provide the IMU measurement noise and bias random walk noise as algorithm parameters. Existing datasets are collected with only one or very few devices, allowing for parameter tuning tailored to each dataset. However, this approach may not be suitable for our dataset, where the IMU noise among the 100 different models of phones varies greatly. We conduct an experiment to analyze whether a unified set of tuned parameters can be generalized to all phone models in our dataset. We run all systems on the so-called dataset using a deviation to compare the two configurations. For tuned parameters, we use the default parameters of VINS Fusion tuned on Europe as the unified parameters for all phones. For calibrated parameters, we use the IMU measurement noise and bias random walk noise obtained from the results of camera IMU calibration as the IMU parameters set for each phone separately. The results are shown. Overall, the calibrated parameters perform better. Finally, we conduct evaluations on the entire dataset using the representative VI slime systems, revealing that the current VI slime methods still have serious robustness issues when it comes to mass deployment on mobile phones. For the first three sub-datasets, all the 100 sequences in the same sub-dataset follow the same motion in the same scene. The performance variation comes from different models of phones. On the simplest circle dataset, the results are relatively consistent, but there are many outliers. On the other two datasets, line and rotation, the boxes are much taller, reflecting the performance variations among different models of phones. We found the main robustness issues for these two datasets. On the one hand, it is difficult to successfully accomplish visual inertial initialization on the low-end phones, resulting in high failure rates or large errors if the algorithm is overly optimistic about the success of initialization. On the other hand, the low-quality IMU causes serious error accumulation, and loops fail to be closed to correct the error. Overall, all of the four systems face serious robustness issues on the proposed dataset. That's all. Thanks for your watching.